Well, it looks like another email made it past the spam filters, which is a little bit distressing. But it was an email from a student, and they were asking about the Friday assignment, the one we're currently working on in the 2D NMR module. And it was a short email, and it basically, said the following. I'm kind of stuck on that nicotine question. I have a few of the positions characterized, but I don't know how to proceed. Can you help? Oh, and P.S. Love the shirts. To be honest, you read a question like that, and I, like almost all professors, have a natural reaction to such a question from a student. And I thought for just a moment about ignoring it, because I of course have lots of other important things to be doing right now. But then I got to thinking that this is one of the frustrations I find in the online format, because this would be a perfect type of question to devote a class to in tackling this thing, and trying to get everybody up to speed on exactly how how do you approach this kind of problem. And so what I decided to do is, as I've done a number of times, is add a supplementary video. This one, because if this class has lacked any one thing, it's me on video. And so here is a little bit more. And so here's what I'm going to do. This will be a little bit crude, but that's okay. We'll get through it. And what we're going to do is essentially, I'm going to try to show you how I approach doing this type of question. Because it will, basically, hoping to model what I do to show you how kind of to get this sort of process started, and the things to be doing and the things to be thinking about. So the first thing I do is I take all the spectra and print them out. I have them here on paper. I naturally just think better on paper. I know I'm old and decrepit. I have them up on the computer screen as well, but I'm going to be drawing lots of notes and stuff on paper here. I have my handy dandy trusty ruler. I've had this one for years. I've used it on lots of NMR spectra. Yes, I love you too. And a pencil. A pencil simply because I'm going to be marking things, and I'm going to be erasing things. I'm going to be writing something and go, and then have to erase and go back and do that sort of thing. So these are the things that I have sitting here in front of me. And the other thing that I'm going to make sure I put together is, I'll hold it up here, but I'll give you a picture of it in just a moment. The molecule, okay? The molecule with its structure drawn, you have this one in the module itself. I didn't even ask you to look it up. But what I did is I numbered it, or I labeled it. Some people like A, B, C, D. I'm a geek, I like 1, 2, 3, 4. So what I did is I numbered and labeled all the positions in nicotine, starting, carbon number 1, and just numbering it, numbering the entire molecule, so I can talk about the proton at position 5 or the carbon at position 5, that type of thing. And our goal is to fill in this table down here with all the chemical shifts of all the different pieces of the molecule, called a complete characterization of nicotine using its NMR spectra. You would want to do something like this if this were a natural product, like nicotine is, potentially a pharmaceutical, biomolecule, and you're interested in how does it interact with other molecules? How does it bind to a protein, for example? Or, what does it do when it's in a certain system, whether it's a living organism or something? And, in order to do that, you're going to be watching for, okay, which atoms are the ones that are interacting. And to do that, you need to know, if you're going to study this by NMR, exactly, which atom is giving every single signal in your proton spectra and your carbon spectra. And so that's why we would want to do a complete characterization, and that's what we're going to tackle now. Now we're going to change perspective here for a moment, because I want to kind of show you how I go about doing this type of thing. And it's going to be a mess down here. You're going to see my hands, but at least you won't have to see me. And so what I'm going to do, what I think the first thing you ought to do when you have your structure drawn is redraw that structure on every single one of the spectra. So I would take all of them and redraw it and put your numbering scheme on it. Okay. Attic, doink, 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 CH3, and I specifically tell us about that position there. And that's position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and what I'm going to do is I'm going to repeat that for the proton, or got it on the proton, for the carbon, for the depth 90, or for the carbon depth 9135. I'm going to put it on the cozy. I'm going to put it on the HSQC. Yeah, it's a hassle, but you've got a lot going on when you're doing this sort of stuff, and it's a good idea to have this structure ready to go and reference every single time. So I'm going to go ahead and do that. So one of the most obvious things that you should begin after getting all the structure written out is I would look at the carbon, and I would go ahead and write in above every one of the carbon peaks, and you notice they're all there: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In a molecule with 10 carbons, they are all present. No symmetry in this thing. That I would mark them as, what kind of carbon they are. For example, clearly, this one over here is a CH2, CH2, CH3, CH2, CH, solvent, and so we can say go away solvent, CH, CH, quaternary carbon, CH, CH. We've written these in on the carbon, and I am going to write them in on the HSQC as well. Okay, yes, it's laborious and takes time, but it will save you much hassle in the long run. CH2, CH2, CH3, CH2, CH, solvent, CH, CH, quaternary, CH, CH. There. All right, now we go after some of the obvious peaks in here, and there are some that should be just so obvious they just reach out and slap you in the face. One of them that pops out at me right off the bat is that quaternary carbon in the aromatic region. There's only one thing it could be. It has to be position 5. There is no proton attached to it, so I can ignore the fact that, I can ignore that there's no proton entry for it. But I look, and it is a bit of an odd scale, I will admit. It looks like at about 139 ppm. Okay, quaternary carbon, not in depth 90, not in depth 135, but here it is, nice and pretty in the regular. So 139 ppm, all right, is the position of number 5. And every time I get one of these characterized, I think it's not a bad idea to go through and mark that fact on your other spectra as well. The next most obvious one in here, I believe, is position 10, the methyl group. Again, this one should just slap you in the face. There's only one methyl group in there, and it's at 40 ppm. Position 10, okay, is at 40 ppm. If we switch over to the proton spectrum a moment, okay, that one, there's a big old singlet. Yeah, it's integrating to, rounding off, it integrates to 4. There's almost certainly an overlapped signal under there, but there's this giant singlet there at about 2.1 ppm. And I'll point out that when we do these things on the HSQC, we don't really need it for this, but this is a good teaching moment, they say. Okay. I know that is position 10, so I mark that. And I know this is position 10, so I mark that. And I want to point out the HSQC, sure enough, shows, if we draw the straight line out from position 10, boink, to hit to its cross peak. We have to make sure it's nice and straight. And then turn and go to the other axis and draw its straight line. Sure enough, those two do correlate with each other. We already knew that, but there's a nice illustration of it. And sure enough, I want you to notice this little dooflaggy right there. That is right near the peak at 2.1. That is probably the one proton that makes the methyl group integrate closer to 4 than it does to 3. We'll come back to that in a moment, but I have gotten these labeled, and yes, it's not a bad idea to label that peak position. I know that one is position 10 here. I also know that one is position 5. Yes, indeed, I know that is position 10. And yes, indeed, I know... Come on, piece of paper. On my cozy, that is position 10. That is position 10. I am being very careful and very systematic in marking every single one of these things as I move along. And so my table now has an updated look to it. And from here, we continue on. Another obvious one, I think, that you could dig around and make a pretty good case for it, is position number 1. Now, there are 4 aromatic protons in this thing, and sure enough, we see them here, 1, 2, and then 2 of them in there. If you look at this particular one for a moment, notice that it doesn't look like a nice pretty multiplet. It's almost certainly 2 different protons just very close together. And sure enough, one of them, the most downfield one of the bunch, looks like a singlet. All the others have some sort of coupling pattern to them. And if you look at structure, position 1, that proton has no neighboring protons. So it ought to be a pretty decent looking singlet. Therefore, I am pretty confident that I have nailed the proton at position 1. It is the, I'll call it 8.5 ppm. And this is where our dear friend, the HSQC, plays a role. Switch over to the HSQC here, and I will look at the most downfield proton. There it is, a little small there. And sure enough, if you come down and correlate, it correlates right there to the most downfield of the protons. Most downfield of the carbons, excuse me. And so I think this is decent evidence that that is position 1 in the proton, and this one right here is position 1 in the carbon spectra. That puts carbon at position 1 at approximately 152 ppm. And keeping everything updated, that is position 1. Okay, and keeping everything updated, I will also say this is position 1. Keeping everything updated, I will make sure I mark this as position 1. Okay, and so there's all of this stuff updated, and I begin again. There's another obvious one, or that should be pretty obvious here. Not on the proton, but sitting on the carbon spectra. And there's the darn thing over there. Looking at the carbon spectrum. And that is position 6. Now, there are 5 total CHs in this thing. We see them in the depth 90. 4 of them aromatic, 1 of them not aromatic. That has to be position 6. That one is should jump right out at you as well. Therefore, we have the carbon at position 6, and its chemical shift looks to be about 68 ppm. Okay, so I'm going to put that in on our table. And now I have to find which proton it is. And this is where the HSQC is really going to help us. Because if I look at the proton spectrum and I look down here at the aliphatic region, the area that's not aromatic, I see 1, 1, 1, 1 with that methyl group over there. 1, and then these look like 2, but you know, kind of bunched up in there. Which one of these resonances is position number 6? That's a triplet, that's a triplet, that's a quartet, that's a God knows whatever the hell it is, but it's something. Which one of these is position 6? Okay, I know it's carbon. Okay, I know which carbon it is. It has to be that one. Okay, so this is where our dear friend, the HSQC, plays a powerful role, because if I know that is position 6, then out comes the magic little ruler again, drawing our lovely straight line. We come to the cross peak, and we stop and we turn, and we go to the other axis on a perfect 90-degree angle. Chunka. There. That must be, I would bet the life of any student in the class, that is the proton of position 6. It is the proton at right there. The proton right at 3. I'm going to call it 3.0 ppm. Okay? That gets us another characterization pretty readily. And so our table is filling up. You notice we have 4 out of the 10 positions. We're 40% of the way there, and we haven't even really broken a sweat yet. And so here's the updated table, and let's continue. One other one that I think is pretty clear, we can make a pretty good case for it, and that is position 9. Of the remaining parts of this molecule, these 3 CH2s, positions 7, 8, and 9, position 9 is the one next to the nitrogen atom, the electronegative nitrogen atom. And so I am going to make the assumption that this is position 9, the most downfield of the 3 CH2s. And that's a reasonable assumption to make. That gets me another characterization here, about 57 ppm for the carbon of position 9. And then we have to find the protons that are attached to it. And once again, our dear friend, the HSQC, is going to play a role here. I'll put in my position 9 mark here. And then we start doing the magic. And I want you to note very carefully as you look at this. You'll notice as I come across it, I'll mark it with a ruler, then pull it away for just a moment. There is not one, but there are 2 cross peaks for the carbon at position 9. There are 2 protons attached, and they do not have the same chemical shift. It's not a huge surprise. We've seen this before. Cyclic molecules with CH2 groups in them. This is quite common. But this one is also a chiral molecule. I specifically marked the stereochemistry there at position 6 when you look up the structure of nicotine. If this thing's chiral, the CH2s nearby are guaranteed not to have their 2 protons have the same chemical shift. They might be really close to each other, they might have the same chemical shift by coincidence, but with no symmetry in the molecule, they cannot have the same chemical shift. And so I'm going to go ahead and mark them, and this also provides a nice explanation for why so many of our protons do not integrate to 2 with these CH2 groups in them. There's a lot of things integrating to 1. There's one of them right there. Okay, and I'll go ahead, hit the cross peak, turn the thing, and come up there. That is one of the positions, one of the protons at position 9. That one looks about 3.1 to me. But I have to mark a second one, because if I continue moving out here, I come on this perfectly straight line to the second cross peak. There is the other proton of the CH2 group at position 9.
Okay, and if I do this one and line it up very carefully, there it is. There's the other one. I'm going to call that position 9. I'll put a little prime on it to make it different from the other one. Looking carefully at the chemical shifts, and that is sometimes easier to do on the proton spectrum. There is position 9. There is position 9 prime. And looking at it carefully, that looks to be right around 2.25. 2.25 ppm. So there is position 9 taken care of. And I'm going to make sure I get that marked everywhere else. Let's see, I have it on that one. I have it on this one. And now 9 and 9 prime. Okay. And over here, 9, 9 prime. Okay. Now the trick is going to be to figure out positions 7 and 8. And this is where the cozy is going to make its contribution to this effort. And this is where I'm about to stop, okay, with this and let you finish it up. But I do want to point out how you step from position 9 to position 8, okay? And we're going to need to go from here, which we now know, over to position 8. What we need to do is get the cozy spectrum. And there's our dear friend cozy. This one has the diagonal already marked. We haven't used it up to this point, but now we are. Because what I'm going to do is I'm going to look for cross peaks at position 9. Okay, and the clearest one I think is this one, not 9 prime, but 9. And here we go. I come out from position 9 and I hit the diagonal. There's the peak on the diagonal. Remember, peaks on the diagonal, they're nice, but they're not in, there's no real information in them. Okay. And so what I'm going to do is kind of ignore that and continue out until I come to an off-diagonal peak. And there it is. But you look at it carefully. Notice how I've labeled it. That is 9 prime. It's no great surprise that one of the protons on carbon 9 is coupled to the other proton on carbon 9. It's a 2-bond coupling. They're only 2 bonds away from each other. Sometimes would be referred to as a geminal coupling. But that one I already knew about. Okay, so that one's kind of irrelevant. But there, right there, that is a new cross peak. And that must mark one of the protons of position 8. Okay, the only other set of protons near, close to position 9. So I take that cross peak, turn, move on up to the other axis, and that must be one of the protons of position 8. Okay? Now, once I have that worked out, and that looks to me like approximately 1.7 or so ppm, okay, I'll verify that over here. That is one of the protons at position 8. Yeah, I'm going to call that 1.7 when I look at that. Drew an 8. That's brilliant. 1.7. Now, my task is this. Okay, where's the other proton of position 8? I wonder how we would find that. I wonder if the HSQC could tell us something about that. And the carbon and the protons of position 7. Those should be pretty clear by this time how that's going to work. Now, somebody's going to point out that we have not done positions 2, 3, and 4. And yes, you could play around with these fancy 2D spectra, but I will point out one other thing to you. Coupling patterns have not suddenly gone illegal because we're doing 2D spectra. One neighbor, 2 neighbors, 1 neighbor. Boy, I wonder if you could make something out of that. So, there you go. There is, I think, a whole lot of hints on how to start characterizing the nicotine spectra and determine where every single proton and every single carbon are in this molecule and relate them to the spectra. So, good luck with it. Have fun.